Hello everyone, welcome back to this playlist, and this is the second video of the playlist on magic squares where we shall prove the Siam method of constructing magic squares of odd orders. So in the last video, what we saw at the last is that this fact that a set of n disjoint traversals on a Latin square of order n can be relabeled to form a new Latin square. So in this video, what I'm going to do is I'm going to actually prove this theorem, prove that this fact is indeed true. Okay, so before getting into the proof, let us have an intuition of that this fact is indeed true. So here you can see the Latin square L1. In L1, I have marked 5 disjoint traversals of this Latin square. So these traversals are marked by various symbols over here. This dash symbol is marking this traversal, that is 3, 2, 1, 0, 4, and the circle symbol has been marks another traversal of the square 4, 3, 2, 1, 0, and there are 3 other traversals, all of which are disjoint. So none of them are overlapping, so all of them are disjoint. And you can easily see that these symbols indeed form a Latin square. This dash, circle, triangle, square, and this cross, they form a Latin square. So is this a coincidence? In this theorem, we shall see that the answer is no. So this is the theorem and proof. So the proof starts like this. We shall assume let L be a Latin square of order n with n symbols. Let the symbols be theta 1, theta 2, theta 3, and so on till theta n. So we shall take L like this. L is equal to this matrix where the elements are marked by alpha 1, 1, alpha 1, 2, and so on. And this first part of the subscript is the row number, second part is the column number. Where alpha ij belongs to this set. Alpha ij has to be either theta 1, theta 2, theta 3, and so on till theta n for all ij in the range 1 to n. And we are being given that this Latin square L has n disjoint traversals. So we shall assume these traversals to be T1, T2, T3, and so on till Tn, which are disjoint traversals of L, and each of them are a set of ordered pairs of the form I comma j, such that both I and j are in the range 1 to n. I is the row number and j is the column number, representing the position of each cell of the Latin square. This cell should belong to the Latin square. And we shall define another matrix L dash to be a relabeling of L with these traversals. Let us see what relabeling means in a second. So relabeling of L with these traversals. So this matrix also we shall represent like this: L11 dash, so until L1n dash. Here also the first one is the row number, the second one is the column number over here. And this is how we represent a matrix with 2 subscripts, 2 elements in the subscript. And a relabeling here means that for all ij from 1 to n, what we shall do is we shall define Lij prime to be equal to phi p if and only if I comma j belongs to Tp. So here I have made T also in the range 1 to n because we have only n sets like this, T1, T2, and so on till Tn are defined. So we shall keep T also in the range from 1 to n. And we shall define Lij dash is equal to phi p if and only if Ij belongs to Tp. And phi p is another symbol, phi 1, phi 2, and so on till phi n are symbols which are used to relabel. These symbols are used to relabel the traversals. Okay. So suppose for some, what we need to prove is that Lij dash is unique. Now we are trying to prove that this Lij dash is well defined and this matrix L dash is well defined. So for that, what the first step we are taking is we want to prove that Lij dash is unique. So let us assume for contradiction that Lij dash is not unique. So if it is not unique for some Ij, that is Ij are in the range 1 to n. So for some Ij, some value, let us say that Lij prime is equal to phi p, and also Lij prime is also phi p dash, where p is not equal to p dash, and also all this 1 Ij p dash are in the range of 1 to n. And if it is phi p and also phi p dash, what that tells us is the ordered pair I comma j belongs to tp, and also ordered pair I comma j belongs to tp dash for p not equal to p dash. That means that tp intersection tp dash is non-empty. But this is a contradiction because we assume that TP and TP dash are disjoint sets. We know that TP and TP dash have to be disjoint. But here we get an element of the intersection. So this is not possible. Hence, this leads to a conclusion Lij dash is unique. Now we shall prove that Lij dash exists. So now suppose Lij dash is not equal to phi p for any p in the range of 1 to n. Lij dash is not equal to any of these. So Lij dash is not equal to phi 1, Lij dash not equal to phi 2, and so on. For some element, for some ij in the range 1 to n. So we are taking a single values for I and j, and we are trying to assume that this Lij dash is not equal to phi p for any p. So what this would imply is that I comma j does not belong to TP for any p, where p is in the range 1 to n. This would mean that the union T1, union T2, union T3, and so on till Tn has at most n square minus 1 ordered pairs, because this I comma j ordered pair is not there. So other than that, there are n square minus 1 ordered pairs. But since even T2, T3, so on till Tn are disjoint sets which have n ordered pairs or n elements each, then we know that n disjoint sets with n elements each should have n into n square elements. This is a contradiction. So our assumption that Lij dash is not equal to phi p for any p in the range 1 to n for some Ij is wrong. So what this means is that the negation of the statement is true. That means Lij dash is equal to phi p for some p. That is p is in the range 1 to n, and also for all Ij in the range 1 to n, this is true. Because we assume that there exists I and j. Here in the negation, we get all I and j. So this means that Lij dash belongs to the set phi 1, phi 2, so on to phi n for all Ij. That means that Lij dash is unique, and also previously we have proved that Lij dash, we have proved here that Lij dash exists, and in the previous one we have also proved that it is unique. So Lij dash is existent and also it is unique. That means Lij dash is well defined for all I and j in the range of 1 to n. That means the matrix L prime is well defined since all its elements are well defined. Now, since we have shown that L dash is well defined, now we shall see that L dash is a Latin square. Suppose for contradiction, let L dash not be a Latin square. So what if L dash is not a Latin square? So we already know that Lij dash belongs to phi 1, phi 2, and so on till phi n. That is, each element of L dash belongs to this set that satisfy This condition implies that the one condition of the Latin square definition is satisfied here itself. And we have other two conditions which a Latin square needs to satisfy. We shall see them. If L dash is not a Latin square, at least one of those two conditions must not be satisfied, right? So in the definition, at least one of the remaining two conditions should not be satisfied if L dash shouldn't be a Latin square. That is, if those conditions shouldn't be satisfied, what we have is, we have for some fixed k and I comma j such that I not equal to j and all ijk are in the range 1 to n. We have L ik prime equals L jk prime equals phi p dash for some p dash. So if two elements in the same row are equal, then L dash won't be a Latin square. And also, if two elements in the same column, this is for same column, this is for same row actually. If two elements in the same column are equal, then L dash won't be a Latin square. And also, if two elements in the same row are equal, then L dash won't be a Latin square. So let us assume condition 1 is satisfied. If condition 1 is satisfied, it would contradict the fact that TP dash is a traversal. Means why it would contradict is because Lik dash is equal to phi p dash implies I comma k belongs to TP dash and Jk dash is equal to phi p dash would imply j comma k belongs to TP dash. So we have both here I comma k belongs to TP dash and also j comma k belongs to TP dash, and I is not equal to j. That means two different cells of the same column are in TP dash, which would mean that TP dash is a traversal. This fact is being contradicted. Similarly, you can see for condition 2 also, this would contradict the fact that TP double dash is a traversal, because the proof is mostly similar over here. We have k comma I belongs to TP double dash and also k comma j belongs to TP double dash, which is, and I is not equal to j. Means two different cells of the same row are in TP double dash. So both 1 and 2 are false. That means all the elements of a row have to be distinct. All the elements of a particular column have to be distinct. And also this condition is satisfied. All the elements belong to this set. There are only n possible symbols over here. And since all the three conditions are satisfied for a Latin square, all three necessary and sufficient conditions are satisfied for L dash to be a Latin square. Hence, L dash is a Latin square, and we have just proved the theorem. Thank you, guys, and I shall see you in the next video where we shall be exploring the Siamese method.